Hello, my name is Selena Mikołajczyk. I'm at Uber Technologies, and I want to thank you for inviting me to come speak on this topic here today. So I'm going to talk about lithium-ion batteries. That's an area I've been working on for about 20 years at various companies. To give you a sense of perspective, lithium-ion batteries were commercialized in about 1993 by Sony Corporation. And at that point, they used these batteries in some very specialized, very expensive applications. They used them in camcorders, which we no longer buy. But they were, a very small product. They were very expensive. And, that's when it started. And then I was working as a consultant at Exponent, and about year 2000 or so, I started taking jobs investigating fires with lithium-ion batteries. And at that point, these batteries were still very expensive, and they were being used in laptops. And, in 2000, a laptop was not everyone's computer. That was an expensive computer for people who could afford to spend quite a bit. And so you had a battery pack, and it might have 100 watt hours in it, maybe. And again, it was a fairly modest volume of products. But at that point, the industry started seeing fires, and that's when I started working in lithium-ion battery safety. Now, to give you a sense, that battery pack 20 years ago, 100 watt hours. Now, when we look at large format battery packs, the price of cells has come down, the energy density has gone up, and we talk about installing battery packs that are in the megawatt hour range or hundreds of megawatt hours. So if we take a look at recent installations of battery packs, we are at a whole different range. And this started to really penetrate the market maybe 2 to 3 years ago. So this is a picture of a solar plus battery installation in American Samoa. And let's see if I can show. That's the battery pack installation there. That's between like 3 and 6 megawatt hours of battery pack, okay? It's a big installation. This installation powers the island. It displaced diesel generation for the island's grid power, which is a really profound application if you think about it, because the fire protection industry knows that when you use petrochemicals, diesel generators, those come with their own problems and their own safety risks. And the folks that are working in sustainability also understand the aspects of the petrochemical industry that that are difficult. But now you're looking at an island that has taken itself off of petrochemicals for their grid. And this is a trend that is only going to continue. This is an installation in Kauai, on one of the islands of Hawaii. These are probably about 100 megawatt hours. Again, a huge solar field, big battery packs. This island is working to get itself off petrochemicals for its grid power. And you can see that in areas where access to petrochemicals is difficult, where you have to bring them in on a ship rather than through a pipeline, and even areas where maybe they're more remote and you don't want to put the infrastructure in, suddenly solar battery packs, wind and battery packs, even hydro and battery packs start making a real difference, and people are going to continue this trend, and we're going to see more and more of these installations. This is an installation in Los Angeles. You notice there's no solar field next to this one. What this installation did was it displaced a natural gas peaking plant and natural gas storage. Los Angeles had an issue with high pressure natural gas storage, safety issue. So they started investing in alternatives. One of those was battery storage for power, so that they can support their infrastructure throughout the day. The previous ones I've shown you are they're Tesla cabinets. I work there, so I know about those. But you can see a lot of players are getting into this, and you see various type of installations like this, and you see more and more of these kind of containerized systems as well. These are very big energy storage facilities. They're also very quiet. They don't require any maintenance. They're very cost effective, okay? And so they're going to be very, very popular as we go forward. We're using batteries for our grid storage. We're also using them for our transportation. Now, we all like to look at pictures of burning electric cars. I do too. I wanted to show you, first of all, electric car that is not on fire. That is actually, that's my Tesla. Okay, I own one, and it charges inside my garage every night. So I will show you some pictures of fires and fires with electric cars and lithium-ion batteries. Please understand, I own one of these, and I have enough confidence to actually use one of these consistently. Um, the reason, and the other thing that I want to bring out is the reason we bought this car is not just professional pride that this is my industry and I will support it, but we bought this car because it has profoundly greater safety performance than an internal combustion engine-driven car. Because the battery pack is a skateboard under this car, it is almost impossible to flip this car over. Okay, its performance in crash is also rather remarkable because there's no front engine in place, so the crumple zone on this kind of car is much better. So what you see is, you can look at this from a sustainability perspective, you can look at this from I'm going to get away from petrochemicals, but also from a perspective as an owner, which car do I want to put my family in? An electric car can have a much better safety performance than an internal combustion engine car. Okay, so that, again, you're going to see a trend to electric vehicles for a lot of reasons. That are often overlooked. Okay, and also from a perspective of safety for first responders, when you respond to a lot of vehicle crashes, you see a lot of injuries. These cars have the lowest probability of injuring the driver or passengers of anything on the road, which is that's a substantial thing. Okay, also. People like to take pictures of burning Teslas, and I complain at conferences when people show pictures of burning Teslas. I'm going to go and show you some pictures of burning Teslas. But fires with these electric cars are much less likely to happen than with internal combustion engine cars, so you should keep that in mind. We're looking at this with cars. We're also looking at this now with semi-trucks. And semi-trucks are very interesting, particularly in the United States. A lot of the cargo around the country is moved by these vehicles. The fuel costs on these vehicles are immense. There's the promise from a number of potential manufacturers to make electric semi-trucks. They cannot produce these fast enough or get the technology out there fast enough. They are being pre-ordered by the industry because of the potential savings in transportation costs. So we're going to see a lot of these. And then this is the future. This is where I work at Uber right now. We're developing electric aircraft, vertical takeoff and landing for air taxis for cities. These are small aircraft. They'll take about 5 people. The battery pack we project in this will be about 150 kilowatt hours. The Tesla I showed you was 85 kilowatt hours. So it's not that much bigger than a battery pack in a car. But this is something that we see that we're going to have in the future. And my feeling on this is if we can make an electric aircraft like this, there's not going to be internal combustion engine cars on the ground. This is going to be the future. So what do we need to protect? Well, some of the things we've talked about. Energy storage systems, we can have problems with those. The picture you're seeing here is a facility that was in Arizona that about a month ago had a severe incident. There was an explosion. 4 firefighters were injured and taken to hospital, 2 of them critically injured. That's a real issue that we need to address and understand. We need to talk about vehicles. That's the iconic picture that I see at every conference of burning Teslas. I used it too. There are other electric cars that have had fires and people have caught them. They do not happen that often, but at the same time, we do have to be aware of this, and we also have to be aware that cars, even internal combustion engine cars now, are a little different. And our codes and standards were really written with the cars of the 1950s, 1960s, 1970s in mind. They do need to be updated in general. So we also need to think about our parking areas, our charging areas. We also have to think about production facilities. People are making these battery packs, and there's not very good code for lithium-ion batteries. That's something that NFPA has been working very hard on, also the insurance industry, but it's very difficult to define what kind of a sprinkler protection you would use in a production facility. And then recycling infrastructure is a new thing too, that we're seeing. People have recycling plants and they start having fires in them, and they realize that people are throwing their lithium-ion batteries into the trash or into the recycling bins, and that's caused a great deal of loss. And that's something where we have to address as well. Okay. So first step, what should the OEMs, the original equipment manufacturers, do? When you're designing a laptop battery or cell phone battery, all of us have seen the videos of these. They can have a pretty big fire, but it's not that big a fire. Okay, when you take a look at a vehicle or an ESS that catches fire, that's a potentially much bigger hazard. So you have to design those systems with the idea that you will have cells that will go into spontaneous thermal runaway. When I was still a consultant in about 2006, I visited Tesla. I was a consultant and I looked at their first design and I said, you know, you're going to burn about 1 in 10,000 cars to the ground. And they looked at me and they said, what do you mean? And I said, well, industry typically sees about 1 in a million cells just spontaneously catch fire. The industry record has gotten better since then. But the problem remains that you do have spontaneous thermal runaway failures that they're not really spontaneous, but they look that way. And so you have to assume if you're going to have a system where you're going to have 1,000 cells in the battery pack, 10,000 cells in the battery pack, 100,000 cells in the battery pack, the chance that one of those cells will suffer a thermal runaway failure is substantial. And so you have to design for that. And what you do is you design propagation resistance into your battery packs. To the guys at Tesla's credit, you know, they thought I was a giant pain, but they went out into the desert and burned some battery packs, and they realized, propagation, it's an important thing. And then they started designing for propagation resistance, and they led the industry doing propagation-resistant battery packs and have been pushing that concept for a long time in the industry. So you have to do that, but then you also have to assume, well, there will be situations where propagation resistance is not enough, where you will overwhelm that for any number of reasons. And at that point, you do need to know how your battery pack is going to burn, and you have to design for that. Because you cannot have a battery pack where if you start an uncontrolled thermal runaway in there, you have an explosion. Okay? You don't want something where cells are going to come rocketing out of your battery pack and pose a hazard to first responders or to try to spread a fire. So you have to also design your battery packs assuming that they will be attacked by fire or they will have a bigger fire. Okay, that's a very important thing for an OEM to do. To do that well, the OEM has to do full-scale testing. And you know, this is daunting when you look at these containerized systems for ESS and you propose to these manufacturers that they take and burn a container. They look at you like you have two heads and they ask if you're crazy. It is a difficult thing, but at the same time, if you don't fully understand what will happen in that container, and that's difficult to do with benchtop simulations, and it's easy to fool yourself with a benchtop simulation to think, oh, you know, I can control this well enough, I know what I'll do. You really need to have burned one of these at some point in time and really understood what will happen. And I think that was probably one of the issues with that Phoenix incident. They had suppression in the container, but they hadn't really thought about what they would do after that fire was suppressed, where it was still smoldering inside, and then eventually someone had to go open the door. And it was after the firefighters opened the door, and they'd been on scene for like an hour, seeing smoke kind of coming out of some switchgear, and they had to open the door, and they wanted to go in and suppress the thing. Well, that's when they had the explosion. Okay, so when you run full-scale testing, you do discover some of these things that maybe you hadn't really thought about beforehand, that you know then you have to plan and design for. Okay. The other thing an OEM should do is prepare the proper emergency response guides and think about, you know, who's going to be responding to my unit and what are they going to do. You know, sometimes people do SDS. A battery is not really a material and it's kind of unique. And really you need to provide the first responders an appropriate guide for how they're going to address your battery pack. Okay. Going along with that is an OEM is really obliged to provide a strategy for removing stranded energy. Okay, if you have a battery pack that, for example, gets damaged, it's involved in a crash, someone runs into a stationary ESS with a truck, a forklift, and they damage the battery pack. Now you have a damaged battery pack that you may not be able to discharge electrically. How do you deal with the stranded energy? How do you decommission that piece of equipment? What's your plan? There has to be a plan. If you don't provide a plan, you're really only doing half your job. Okay? And then finally, you have to have some recycling plans, and really the industry needs to support the standards process for developing some of these more advanced standards. Now, OEMs cannot address this issue on their own. This is something that, we're going to see more and more of these battery packs. And there's going to be a number of low probability events that are going to crop up that, that are just going to have to be handled by the fire service. For example, natural disasters. So this, I don't know how many people remember the Fisker Karma. The Fisker Karma. It was a nice car. It was a very beautiful hybrid electric car. The company had about a little more than 300 of these parked outside of New York City, and the superstorm Sandy occurred. And what that did was it flooded these cars. They got flooded by a mixture of salt water and mud. They were a total loss. They also had a low voltage system that was susceptible to short circuiting, and a few of them, as the water receded, started catching fire. And it wasn't the high voltage batteries that caught fire, it was the low voltage systems that started these fires. Battery kept the power going to the low voltage systems. They had a number of fires, and then they had to dispose of all the rest of these cars, which were water damaged and potentially could have a fire. Okay, you don't have a superstorm that comes through and floods your entire inventory very often, but it does happen enough. High-speed collisions, we test for there are certain regulatory requirements for collision. There are faster collisions that occur, and just strange accidents that you didn't design for because they were so far out of expectation. Arson. I've seen, I investigated when I was at Tesla. I investigated any number of fires, saw a few which were arson, where someone tried to light the car on fire. It happens as well. Your battery can be adjacent to another fire, and it can sustain heat damage from something else. At that point, you have a damaged battery that you need to address. Something else I saw when I was at Tesla where people were deciding they wanted to try and repair the battery pack themselves, or there were little small companies that were coming in to refurbish the battery pack, or there were hobbyists who would buy totaled cars on the internet and then take the battery packs out and try to create their own little projects for those battery packs. They might be home stationary systems. They might make another car. They might do any number of things. A lot of these people did not really understand the hazards that were associated with the battery packs. It was always terrifying to watch the YouTube videos, and I'm watching them do things, and I'm wondering where the high voltage gloves are, and they're just kind of digging into these battery packs that are 400 volts barehanded. It was eye-opening. Okay, and then we're also seeing something. We're seeing something at Uber with the small bicycles, electric bicycles, that people are stealing the battery packs, disassembling them, and selling the cells on the black market for profit. Again, all kinds of things happen out in the world. People are very creative. So a few questions that I often see from the fire service that I wanted to address with you. The first one is, how does a fire crew know if there's a problem? You come to a site, someone has claimed they smelled something, they saw something. The best indicator is smoke. Okay, a lithium-ion cell is hermetically sealed. It is not sending any gas out to the outside world in normal operation. The only time you have gas venting out of a lithium-ion cell is if it is overheated inside and it is starting to vent. And that vent temperature on that cell, by regulation, by the UN transport regulations, is somewhere above 150 C. So if that cell has exceeded 150 C, you will see smoke out of it. You will not see smoke out of a cell otherwise, unless someone's done something like punctured it. Then you might see some venting things. But if you walk up and there's no hole in the battery pack and there's smoke coming out the top, you know you have a problem. Okay. The other thing you need to be aware of is that smoke is flammable. It may contain it may also contain some fraction of hydrogen, which makes it very ignitable. Okay. This is recently from Shanghai. This was an incident in a parking garage. This was a Tesla that caught fire. You can see the smoke, and then it ignited. Okay. So smoke out of lithium-ion battery packs should not be ignored and should be assumed to be very flammable. The good news is that it is very easy to detect this smoke. A standard smoke detector that you can buy in a hardware store is very adequate to detect that. And it will detect it before you can see it. Okay. That's a full-scale test that we did with NFPA, a power pack, and that's the smoke coming out of that power pack. It's designed to produce the smoke upwards rather than out toward anyone that might be on the ground. Another one is, can we use water? Yes, water is very appropriate for lithium-ion cell fires. Um, it will suppress flames, it will protect exposures, it will cool battery packs if you can get it into a battery pack to actually cool the cells. Sometimes that's difficult. Um, People will periodically want to try to use a lithium metal extinguisher on a lithium-ion battery. That is a very bad idea for two reasons. One is it will not work. Okay, it is not designed for that. And number two, lithium metal suppressants, they work by melting and encapsulating the lithium metal to separate it from its oxidizer. Okay, that's what works with lithium metal. That action can actually make lithium-ion battery fires kind of worse, because if you've got vents and vent paths that you're planning, that your cells are you're planning to have your cells vent through, if you start clogging those with material that kind of melts and starts sealing them, you could have a worse problem than if you just let the whole thing burn. Okay. In some cases, I recommend CO2 extinguishers. For example, in a factory situation, you're building battery packs. You have a lot of electrical equipment. You want people to feel like if they see smoke, they can grab an extinguisher and apply it. It will cool the cells down, and it can give you a lot of time to react in other ways. It's effective. It's not as effective as water. Okay. But something else that we should consider is if you've got a properly designed system, you might consider letting it burn, particularly if you can effectively protect the exposures. And the reason for that is it is substantially easier to clean up a fully burned lithium-ion battery pack than a battery pack with stranded energy. It's substantially easier. Okay, so you know this is a balance that needs to be addressed. Now, some cases you can do that, sometimes you can't. Does the fire pose unique hazards? Yes, it does. Not necessarily the ones people worry about. The smoke that's released from a lithium-ion battery, even when it's smoldering, can be very flammable. And you might have the flame suppressed, but your propagation of thermal runaway may be continuing, and you're producing a lot of smoke that can still be a hazard. So you need to consider that. Depending on how your pack is designed and how your cells are designed, you might have some jetting flames that can occur. If you have a poor battery pack design too that does not constrain your cells, you can have cells that will start rocketing away from the battery pack and spreading fire to surrounding areas and being a hazard to first responders. That's important for designers to continue to consider, and it's something that the Fire Protection Service needs to consider as well. There's a lot of reignition potential. If you've got, again, a properly designed battery pack where you fire blocked to slow down reactions, to make sure that reactions are fire might be well behaved, that will have a tendency to slow down the whole progress of the fire. So you would have lulls of maybe like, you might have a module catch fire, you see flames, that stops for about 15 minutes, and then you catch the next module that'll reignite. And we saw this where, fire service shows up, they see the flames, they apply water, things seem to stop, they apply more water, and then the next module catches fire, and then they suddenly think the water made it worse. The water did not make it worse, but this was the latency that was built into the system. Again, this is why full-scale testing and reviewing full-scale testing in the fire service is so important, because if you haven't seen this before, it is very surprising. Okay. Something that people ask me about is toxicity of the smoke. I've studied that. NFPA has studied that. People worry about hydrofluoric acid in the smoke. From the studies that I have done, you're more likely to encounter HF in electronics fires from the insulation on the wiring than you are out of lithium-ion batteries when they're burning. Some of that's going to be dependent, obviously, on how people handle their battery packs, but this is not something that's a big issue with these. The flames are at regular flame temperatures. The smoke is flammable. That is the biggest hazard. Okay. Next question is, how do we clean up the mess? Usually when you come to a fire, you worry about, suppressing the flames and then doing an overhaul. It's a really bad idea to go with an axe and start trying to overhaul a lithium-ion battery pack. I really, really hope people don't do that. What you have to consider with the lithium-ion battery pack is, can you assess, is there stranded energy, and what's your plan to get rid of it? Can you let it burn? Is that your way to get rid of the stranded energy? Can you discharge it electrically? Or what my companies have tended to use is a dunk tank method where you submerge the battery pack, but you have to then let it corrode in the water. That will take days, if not longer. And dunk tanks have their own unique hazards associated with them. So you have to be careful. You have to know what you're doing if you're going to try and do a dunk tank approach. Now, the German fire service posted this depiction of a dunk tank. They took a car, put it on a crane, and then submerged it, the entire car. That's not the way I would do it. Okay. There's some hazards with submerging an entire vehicle and a vehicle which might have a 400 or 800 volt system, putting the whole thing underwater for a number of days is difficult. There are better ways to do this, okay? But to do this better, you need the OEM's support, and you need the OEM to have worked out how they're going to do a discharge for this, okay? And then finally, you have to consider how you recycle the debris. Even if you've got a burned battery pack, you don't want to be just dumping that into landfill. You want to be sending cell bits to recycling. And if you've used a dunk tank, you take also the water and you treat that as waste appropriately, okay? So just to finish, we're going to see a lot of large lithium-ion battery packs. There's a lot of good reasons for that, a lot of benefits, both for stationary and for vehicles. But they do pose some unique risks, and this is a new technology that we're not used to. Petrochemical industry, we've had 100 years of experience with. We know how to deal with lithium-ion batteries, really the large format ones. We haven't seen these for more than about 5 years. So there's a lot of learning, a lot of training that has to happen in the near term. The OEMs can play a large role in this, and they should. And then my other takeaway is that full-scale testing is very important. As daunting as it may seem, NFPA has led on this. They've run vehicle tests. They've run ESS testing. They've worked with FM Global recently on warehouse and sprinkler testing. There are requirements for full-scale testing in the newest standard for energy storage systems. If you want to go over certain thresholds, you have to do the full-scale testing to prove that you actually understand what the system will do. The biggest hole that I see right now is that the methods for controlled release of stranded energy have not been well established. If you've got a group that's been doing this a while, people know how to do this, but it's not been something that's been promulgated to the industry. Okay? So thank you.